Welcome back to the deep dive. Today, we've got a really interesting stack of research focused squarely on Stellantis. They're talking up a new EV technology they call IBIS, that's Intelligent Battery Integrated System. Sounds pretty important.
It does, yeah. And our job today, really, is to cut through the buzzwords. Automakers love calling things game changers, but we need to look at the actual engineering
Yeah.
because the sources suggest this isn't just a minor tweak to a battery cell. It looks like a fundamental shift in how the whole electric powertrain is designed.
Right. And Stellantis, I mean, they're a huge global player. When they make a big move like this, it really could ripple through the whole industry. And honestly, as someone with Italian roots, seeing Stellantis pull off something really groundbreaking like this, well, it makes me genuinely proud, thinking about the history of those brands.
Oh, absolutely. And look, when you're excited about a tech leap, I get excited too, because it means it's something genuinely new and useful for everyone listening, adding to their knowledge base. And the hook here, the really interesting claim, is that IBIS gets rid of two major expensive components in the EV. That definitely caught my eye. Okay, let's dig into it.
Yeah, let's start with the basics. Every EV has this kind of core issue, right? The AC-DC problem, battery store DC, direct current.
Correct. But then you've got the motors, which need AC, alternating current, to run effectively. And complicating things further, when you plug your car in at home, the grid gives you AC power. So you absolutely need this sort of translator in the middle to handle both directions.
And that's the job of the inverter and the onboard charger. Usually they're these pretty chunky, complex boxes. They have to handle really high voltages, like 400 volts, sometimes even 800 volts, and a lot of current switching back and forth.
Exactly. And those components, they add cost, quite a bit of weight, they generate heat you need to manage, and honestly, they're often a point where things can go wrong. So IBIS, the Intelligent Battery Integrated System, the big idea is to basically absorb those functions, the inverter and the charger, right into the battery pack itself. It's all about integration leading to simplification. Stellantis' chief engineering officer, Ned Keurig, put it quite well. Simplification is innovation.
Okay, conceptually that sounds great. Simplify things. But practically,
Okay.
how do you stick conversion circuits inside a battery module? Aren't you just shifting the weight around? Or worse, creating a major heat problem right next to the cells?
That's the million-dollar question, isn't it? And it gets to the heart of what makes IBIS different. They do the conversion locally. So instead of one big central inverter pulling all the high-voltage DC power out of the pack, IBIS works at a much smaller scale. It takes DC power from just a small group of cells, like a little cluster, and converts it to three-phase AC right there.
Right there within the module electronics?
They use a specific electronic circuit called an H-bridge for each cluster. You can think of it like a set of super-fast electronic switches. They rapidly flip the polarity of the DC current coming from those few cells, which effectively chops it up and shapes it into the AC waveform the motor needs. The key thing is, the voltage being handled at that point is only the voltage of that small cell group, not the full 400 or 800 volts of the whole system.
Okay, but putting high current switching circuits, even smaller ones, right next to battery cells, that still sounds like a thermal risk. Heat is the enemy of batteries, right? Lifespan, safety.
Yeah.
How did they solve that? That must have been a huge challenge.
Absolutely critical factor, and the sources do touch on it. They spend a lot of time, it seems, optimizing this trade-off between heat, cost, and space. Because the heat generation isn't concentrated in one big box anymore, it's spread out across many small points. They don't spell out the exact cooling methods, but the prototype success suggests they managed it, likely through very clever circuit design and maybe localized cooling within those cluster electronics.
Okay, distributing the conversion makes sense from a heat perspective. But what was the specific configuration they landed on? You mentioned clusters.
Yeah, and this is where the specific engineering detail comes in. After a lot of R&D, they found that grouping cells into clusters of 6 was the sweet spot, 6 cells per conversion circuit. Apparently, that specific number gave them the best trade-off between cost, packaging space, and managing the heat effectively. They probably looked at doing it per cell, but the cost and complexity just ballooned,
Oh,
6 seemed to hit that optimal point.
6 cells. That level of detail suggests this wasn't just a simulation. They actually built and tested this, right? There was a prototype.
Definitely. They moved beyond the lab. The tech was put into a real development vehicle, a Peugeot E3008, which uses their STLA medium platform. And that gives us some concrete numbers to look at. The really eye-popping result, the IBS version of the E3008 used a smaller battery pack, 65 kilowatt hours, but it achieved the same driving range as the standard car, with a larger 73 kilowatt-hour pack.
Wait, say that again? Same range with, what, 8 kilowatt-hours less battery? So just by changing the architecture, removing those conversion losses, they effectively gained the equivalent of 8 kilowatt-hours of usable energy. That's seriously efficient.
It really is. And it shows this isn't just theoretical. It also underlines that this was a big collaborative project. The sources mentioned it was a French-based research effort coordinated by Stellantis, but pulling in partners like Saft, the battery company, owned by Total Energies, plus engineering specialists and French research institutions like CNRS and Université Paris-Saclay. You don't pull together that kind of team unless you're serious about the research.
Okay, so the prototype proved the concept works. Let's get into those hard numbers then. What are the confirmed benefits? Efficiency, power. What did they actually measure?
Right. The confirmed metrics are pretty impressive. First up, efficiency. They're claiming up to a 10% improvement in energy efficiency measured on the standard WLTC test cycle. And apparently it's even better in city driving conditions where there's more stop-start and regeneration.
10% is massive in the EV world. Every percentage point counts for range. What about power output?
Power gets a boost too, a confirmed 15% gain. And that's purely from removing the electrical bottlenecks and losses associated with that big external inverter. On the prototype car, that translated to a jump from 150 kilowatts in the standard version to 172 kilowatts with IBIS. Same battery cells, just unlocked more power, faster acceleration, better performance.
And better efficiency directly means less weight needed, right? That's always the goal.
Always. Two savings here. First, the obvious one. You take out the separate inverter and charger boxes. That saves you about 10 kilograms straight away. But the bigger saving comes from the efficiency gain itself. Because the system uses energy better, you need less actual battery material, less electrochemistry to hit your target range. That accounts for another roughly 30 kilograms saved.
So 40 kilos total. Wow, that's like taking a teenager out of the car weight-wise. Significant.
It really is. And then there's the space saving, about 17 liters freed up. That might not sound huge, but in car design, that's valuable real estate. It could be more cabin room, or they could optimize the car's shape for better aerodynamics, which again helps with range, especially on the highway.
Okay, those are clear wins for the engineers and designers. But what about the person driving the car? Does it charge faster? Is it more reliable?
Good questions. Yes, benefits there too. That efficiency improvement helps with charging speed. The numbers suggest about a 15% reduction in charging time. So think about plugging in overnight on a typical 7 kilowatt home charger. If that normally takes, say, 7 hours, IBIS could cut that down to about 6 hours, a full hour saved on your regular charge.
An hour off the overnight charge is definitely something you'd notice.
Nice.
But reliability. Okay, you remove one big complex box, the inverter, but you're replacing it with dozens of these little H-bridge circuits inside the battery modules. Doesn't that just create more potential points of failure? Seems more complex in a way.
Intuitively, maybe, but Stellantis actually claims the opposite. They're projecting 3 times fewer breakdowns. And the logic makes sense. Redundancy. Because the conversion is distributed and modular, the system is more resilient. If one of those small clusters or its circuit fails, the system can just bypass it. The car might lose a tiny fraction of its total capacity or power, but it keeps driving. Compare that to a failure in the main centralized inverter today that usually means the car is completely dead, bricked on the side of the road. So it's a potentially huge reliability gain.
Okay, that makes sense. Resilience through distribution. So IBIS clearly offers benefits for current EVs, but reading between the lines, this sounds like it could unlock future potential too.
Absolutely. This is where it gets really interesting long-term, moving beyond just efficiency. The sources explicitly say IBIS has mixing chemistry in its genes. Because it handles the AC conversion locally, at the cluster level, the system doesn't necessarily care what kind of battery chemistry is in each cluster. It's potentially chemistry agnostic.
Chemistry agnostic. Okay, what does that let an automaker actually do?
It lets them mix and match battery types within the same pack. Imagine combining, say, some modules using LFP chemistry lithium iron phosphate, known for being durable and lower cost, maybe for the bulk of your everyday range, with other modules using NMC nickel manganese cobalt, which offers higher energy density and power for bursts of acceleration or peak performance. You could tailor the battery pack precisely for cost and performance using the best of different worlds, all managed by the same IBIS system.
Wow, okay. That opens up huge possibilities. And think about maintenance. If a module fails years down the road, they wouldn't need to find an exact replacement with maybe outdated chemistry. They could potentially slot in a newer generation module and the owner might even get a range boost from the repair.
Exactly. That's a massive benefit. It dramatically reduces the problem of supporting old battery types and offers a genuine upgrade path for the vehicle over its life. Much more sustainable.
Okay, let's switch gears slightly. Charging. You mentioned faster AC charging, but the sources hinted at something more revolutionary.
They did. The theoretical potential here is pretty wild. IBIS architecture could, in theory, support AC charging at powers up to 200 kilowatts.
200 kilowatt AC. But isn't that firmly in DC fast charging territory today? You need those big, expensive DC chargers for that kind of speed.
Precisely. The advantage would be efficiency and cost. With IBIS handling the AC to DC conversion inside the car at the module level, you wouldn't need the complex, costly, and sometimes inefficient AC to DC conversion happening at the charging station itself for DC fast charging. You just feed high-power AC directly to the car. Fewer conversion steps mean less wasted energy, potentially lower charging costs. However, this is a big however, the project director, Demand, points out that this needs completely new infrastructure. We don't currently have plugs or standards for 200 kilowatt AC charging.
Ah, okay, so the tech might be capable, but the plugs literally don't exist yet. So Stellantis is essentially laying the groundwork, betting that maybe one day we'll have super high power AC charging, but that's a long way off. Requires industry agreement, new standards,
Yeah.
a huge lift.
A huge lift, exactly. Which is why, realistically, they're focusing on the immediate wins first, the efficiency, the weight savings, the faster standard AC charging, while kind of holding this high-power AC capability in reserve for the future.
Makes sense. So zooming out, this IBIS architecture seems incredibly flexible. Does it have potential beyond just cars?
Yes, definitely. If you think about the core concept, integrating power electronics directly with battery modules, it's very scalable. Stellantis themselves mention potential applications in things like trains, maybe aerospace, marine use, and significantly stationary energy storage for the grid or homes. Having AC capability built right into the battery module makes using Second Life EV batteries for home storage, for example, much simpler and cheaper. You wouldn't necessarily need a separate, expensive external inverter.
So it's a more fundamental building block for electrification, not just an automotive part, a simpler, more adaptable component.
That seems to be the vision. But we do need that reality check on timing. The prototype is promising, proves the concept works, but it still needs more testing, more validation, especially in extreme conditions, and adapting it for things like complex all-wheel drive systems. Stellantis is targeting availability in their production cars by the end of this decade. So we're likely looking at the 2030s before this becomes widespread.
Right, so it's a clear direction, a major architectural shift towards simplicity and flexibility, but not something you'll see in showrooms next year. Still, very exciting.
It is. And it leaves us with a really interesting thought to ponder, doesn't it? If IBS truly makes mixing battery chemistries easy, combining, say, LFP for endurance with NMC for punch, how might that ability to mix and match change the whole pace of EV development? Could it reduce the huge financial gamble automakers currently take when committing billions to just one specific battery standard? Does it make innovation faster and less risky?
That flexibility, avoiding being locked into one chemistry, yeah, that could be a very powerful advantage in such a fast-moving market.
Food for thought, indeed. Well, thank you for sharing all those sources and helping us really get under the hood of this IBIS technology today. It feels like a genuine step forward.
My pleasure. Always fascinating to see real innovation happening. Thanks for joining us.
And to everyone listening, we hope you found this deep dive valuable. Please do follow the channel so you don't miss our future explorations into the tech and research shaping our world. We'll see you next time.